do my best to talk about these aspects I know a little bit about, and these are in particular her two articles, the one from 1933 and the one from 1935. 10 years ago, roughly 10 years ago, there was the famous meeting about Grete Hermann in Aberdeen, organized by Guido Bacigalupi. And at that time, I used the following slide as an introduction to my talk. Louisa Gilder's book, The Age of Entanglement, had appeared a few years earlier. I think it's from 2008. And in that book, she writes the resulting paper, and now she refers to the 1935 paper of Grete Hermann. The resulting paper in its most widely read form ended up in the pages of Die Naturwissenschaften. This was a dialogue that mathematical formulae were deemed to inhibit, and Grete's incisive passages on Neumann were left out. Nelson's Neo-Kantian journal, it has been mentioned several times, the Abhandlung der Friesischen Schule, also printed the paper in its entirety, but this was hardly a place where the devotees of von Neumann's defective proof were likely to ever discover it. Now, to which extent Neumann's proof is really defective, I will say a little bit more about in my talk and what Grete Hermann's contribution really was. But Louisa Gilder then proceeds that thus it was that no one beyond Heisenberg, von Weizsäcker, and Grete's embattled circle knew of her dismissal of von Neumann's no hidden variables argument, and none of them, for mysterious reasons of their own, said anything more on the subject. Now, today we know that this is not quite true. At the 2012 conference in Aberdeen, it turned out that there was a copy of her 1933 manuscript, presumably in Dirac's papers, and Guido found in the Dirac archive a manuscript of that. It was lost in 2012. Nobody knew the content of that paper, but afterwards it was found, and it turned out that many more people knew about this 1933 paper because she had sent it to, as we heard before, to at least Bohr and Dirac and others, and it was read in these groups. So many people knew, presumably, about her dismissal of von Neumann's no hidden variables argument. And I think that it's even more mysterious than why nobody ever mentioned it later on. And it was, in principle, until the 60s that her arguments were lost. Now, just to repeat these few dates which we heard before, in 1933, Grete Hermann sends copies of this manuscript, Determinismus und Quantenmechanik, to at least Dirac, Heisenberg, and Bohr. And it's known that not only these three people read this copy, but also people in these groups around these Bohr and Heisenberg, for instance, read this paper, which is already, in my opinion, quite remarkable. I mean, I suppose that many of you get emails once or twice a week, people claiming that quantum mechanics is wrong or general relativity is wrong or whatever. And obviously, her paper made such an impression that people really not only read the paper, but also got in contact with her, in dialogue with her. And in 1934, then, Grete Hermann joined the seminar of Werner Heisenberg in Leipzig. She wanted to learn more physics, in particular more quantum mechanics. And she had many discussions with Heisenberg and the members of his group, in particular, of course, with Carl Friedrich von Weizsäcker. Now, the famous article is the one which appeared in 1935. die naturphilosophischen Grundlagen der Quantenmechanik. And as I said before, there was a long version, which is, I think, about 80 or so pages, which appeared in the Abhandlung der Friesischen Schule. And there was a short version. It's difficult to compare them because the pages have different layouts, but the short version is maybe not longer than 10 or 12 pages compared to the in the layout of the long version. So it's just 10 or 15% of that paper, which appeared in die Naturwissenschaften. So what I'm going to talk about, or want to talk about today, is I would say a few words about the beginning paragraphs of the 1935 paper, where she talks about causality and prediction. And as we just heard, she later made a very careful distinction between these two. So prediction is something different as causality, but in the beginning paragraphs of the 1935 paper, she repeats some things which already had been written in the 1933 manuscript, namely that without prediction, we can never tell whether causality, our ideas of causality are true. So for her, prediction in these first paragraphs is a kind of prerequisite in order to recognize causality. And it's only later in this paper, in the 1935 paper, that she starts to distinguish from prediction from explanation, to explain something. And I will come to that. I will then, in a little bit more detail, enter Grete Hermann's critique of von Neumann's proof. This will be a little bit technical, but I think most of the people in the audience are physicists, as far as I heard. And then I will come to a second subject, which she touches in her paper, the Weizsäcker Heisenberg microscope, which she takes as an example of why quantum mechanics is already complete and doesn't need an extension by hidden variables. And so I will say a few words about that and then come to some concluding remarks. So this is the contents of chapter 1, I mean, of the long paper, the one which appeared in the Abhandlung der Friesischen Schule. And it's divided into 11 paragraphs. And there are 2 more chapters, but they have more philosophical content. This is really, here she touches the physics, the hardcore of physics, of quantum physics. And it's very interesting to see that the first 8 paragraphs are devoted to proving that any claims that hidden variables cannot exist are wrong. So quantum, from the side of quantum mechanics, of course, there were many arguments that quantum mechanics is already complete, that there can be no hidden variables, and it cannot be extended by hidden variables without changing the predictions of quantum mechanics, etc. And she now goes through all these arguments one by one and proves essentially that they all have loopholes and are wrong. And the paragraph number 7, called Der Zirkel in Neumann's Beweis, that's what maybe is the most famous critique of her, where she shows that von Neumann's proof that that hidden variables cannot exist has a loophole. It's not wrong. She explicitly says that the proof is correct, but there's an assumption, and we will go into the details later. And then in paragraph number 8, there is a switch, in my opinion, a very strong switch, from arguing that, well, there is still the possibility that hidden variables do exist, to a new kind of, well, let's say, claim that that quantum mechanics is already complete. It doesn't need hidden variables. And this switch for me is still a little bit amazing. It's sometimes I have the feeling it's a little bit inconsistent. And Guido Bacigalupi and Elise Krull argued that maybe the first 8 or 7 paragraphs essentially repeat what has been written already in the 1933 paper, and that she didn't want to give up these arguments. But I have the feeling that she feels much more safer with these arguments in the first paragraphs than what happens later. But that's a personal impression. But then comes this paragraph number 10, which she uses as an example, and that's the discussion of the Heisenberg microscope, and that's also what I want to enter into. Okay, so let me say a few words about the beginning paragraphs and her opinion about prediction and causality. And she says, for instance, at the end of paragraph 1, and all the translation, all the English texts I have here are taken from the translations of Guido and Elise Krull. The fate of the law of causality, therefore, indeed depends on whether and how far, or according to the claims of quantum mechanics, an in-principle limit is set for possible future predictions. I have to see whether I can, I don't know whether I can, I have some things here on my screen which I can't get rid of. Well, let's see. So the fate of causality here, she says, depends on whether there is an in-principle limit for future predictions. And at the beginning of paragraph 3, she says, or she writes, even if, as we assume here, the formalism will prove itself also in the future, as it has so far, and now it's really a problem that, okay. What prevents us from assuming that through an extensive of physical knowledge, it may be augmented with new formulas and rules that, together with the current formal approach, make precise predictions possible again. And then comes this sentence, everything here depends on answering this question. And this is, again, something which astonishes me, because this sentence is not in the 1933 paper. So she added it here in the 1935 paper, and it seems that it has still a high value for her to find the answer to this question, and not only an answer, but an answer which can save the law of causality. Okay, so let me now come to von Neumann's proof. Again, a little bit of sketch of the history. Von Neumann's book, Mathematical Foundations of Quantum Mechanics, appeared in 1932. And in that book, he gives a proof that an extension of quantum theory by hidden variables leading to dispersion-free states is not possible without changing the predictions of quantum theory. Now, already 1 year later, in 1933, Grete Hermann writes this manuscript, which she sent to Bohr, Heisenberg, and Dirac, in which she criticizes von Neumann's proof, saying that he makes an assumption which is not necessary. And then in 1935, there is this famous article, which has been mentioned several times by now, which was published, and where she repeats the criticism. But as we heard before, nobody really took notice of it. Nobody mentioned it anymore. And it was until the 60s, essentially, that people said, no, hidden variables are not possible, for Neumann has proven it. It was in 1952 when Bohm came up with his guiding wave plus particle. So we have the wave and the particle interpretation of quantum theory, what is now called Bohmian mechanics. And that was essentially theory which repeated or which reproduced the predictions of quantum mechanics. And it indicated that there must be somehow a loophole in von Neumann's theorem. But it was essentially not until 1964 when John Bell analyzed Bohm's model. And also he found his own kind of toy model for spin 1/2 systems, a kind of, a model with hidden variables, which reproduced quantum mechanical predictions for spin 1/2 systems. That John Bell essentially rediscovered Grete Hermann's results without knowing it. It was, I think, Max Jammer who later pointed out that this was already known in the 1930s, that Grete Hermann already discovered that. So as I want to go a little bit into this proof of von Neumann, and in particular, what is Grete Hermann's critique, I want to mention some preliminaries. So, which I think in physics are generally accepted. A pure state is mathematically represented by a wave function phi. I don't want to enter now discussions about whether it's a ray in Hilbert space, one-dimensional subspaces, or normalized vectors or so. Let's say a wave function phi represents mathematically a pure state. And in physics, I mean, if we come to reality, not the mathematical formalism, such a pure state is realized by an ensemble of systems which have been prepared equally, which have been prepared in the same way. For instance, by making certain maximal measurements and prepare them as eigensystems or eigenstates of certain maximal set of observables. Now, von Neumann and Grete Hermann distinguish between observables, which are just measurement instructions or measurement protocols, and the mathematical representation of these observables, and that is by Hermitian operators. So the first ones, the abstract measurement protocols, are indicated by this Gothic style letters, and the Hermitian operators, the mathematical representation of these objects, are normal letters. Then R of R, ERWR, ERW stands for expectation value, Erwartungswert, denotes the expectation value of the observable of R in an ensemble S. And that is a number, and that is the number we will now be concerned with. And quantum mechanics now says that for every ensemble S, which we can prepare in quantum mechanics, there always will exist observables for which the measured values scatter, which means, in other words, the corresponding states are not dispersion-free. And this, for Grete Hermann, was a violation of the principle of sufficient reason, and not only for Grete Hermann. This is in principle a violation of the principle of sufficient reason, because we have prepared S in such a way that there are no distinguishing features anymore. All these systems are prepared in the same state, and then they should also give the same results, unless this principle of sufficient reason is violated. So the question now is it possible that hidden variables exist such that if we knew about them, this would allow to partition the pure quantum ensembles further into dispersion-free ensembles? And von Neumann transforms this question into a mathematical question, which is, are there expectation value functionals? And I will say a little bit more what exactly is an expectation value functional for von Neumann, which are dispersion-free. So this is the essential question of von Neumann. And now I will give a brief sketch of what von Neumann's proof is. He makes essentially three assumptions. The first assumption is the linearity of the expectation value. So the expectation value of the sum of two observables should be equal to the sum of the expectation values. And this is the one we will talk about. This is a critical one. He makes the assumption that the expectation value for quantities which always give non-negative results are themselves non-negative, the positivity condition. And although von Neumann relaxes that also, we can say the expectation value should be normalized. That is, for the identity operator, the expectation value should be 1. Now, the first assumption already, the linearity, tells us that this expectation value functional has to be, in modern language, von Neumann doesn't use it in that way, has to be an element of the dual space of a vector. Because Hermitian operators, the observables, the mathematical representation of the observables, they form a vector space. So then if such a linear functional is given on that vector space, it is an element of the dual space. And the other two conditions tell us essentially that the expectation value functional is a density matrix, as we would say in modern language. Again, this is not the language which von Neumann uses, but this is his consequence. Expectation value has to be a density matrix. And next, he proves that pure states can be represented by special density matrices, which are what we call projection operators. And in this case, the expectation value of an observable A is given, as we all know, by the trace of this observable times the projection operator, which represents the state. So this is what he proves. And then he uses a continuity argument that for any state, there exist observables. Again, for instance, projection operators would be an example, for which the expectation value can neither be 0 or 1. And that means essentially that if for any state there exist observables that such that these states are not dispersion free. So that is von Neumann's argument. Now, what does von Neumann say about this linearity assumption which he makes? It's not that he makes it and isn't aware that there's a problem with it. So he writes explicitly, when the quantities R and IS are simultaneously measurable, then this equation, expectation value is linear, is true more or less by definition. And then he writes explicitly, for not simultaneously measurable R and S, the sum is not defined. So he's well aware of that. And a few lines later, he writes, dass wir es nur, or that we formulate it, so the linearity postulate, only for simultaneously measurable quantities R and S is obvious. Otherwise, R plus S and so on is meaningless. So he's well aware that this R plus S, this requirement, can only be in principle formulated on this level for quantities which can be simultaneously measured. But then he makes a twist. Then he says, or writes, in the mathematical formalism of quantum mechanics, observables are represented by Hermitian operators. And the sum of two Hermitian operators is again a Hermitian operator, so can again be interpreted as an observable. And for Hermitian operators and the expectation values in quantum mechanics, which I have written here in the bracket notation, linearity holds. And then he writes this sentence, which he doesn't comment on anymore then. Diese Tatsache übernehmen wir in unseren allgemeinen, vorläufig noch gar nicht zur Quantenmechanik spezialisierten Ansatz. So we adopt this fact for our general ansatz. I'm sorry. And now Grete Hermann's analysis of this. She writes, again, the translation is taken from Guido's and Alice's text. Well, the expectation value thus defined by means of an ensemble of physical systems, which assigns to a number to every physical quantity. Neumann assumes that the expectation value is linear. In words, she repeats it, the expectation value of the sum of the quantities is equal to the sum of the expectation values of the two quantities. Neumann's proof stands or falls with this assumption. And then, she goes on and writes, the relation is, however, so this linearity condition, not self-evident for quantum mechanical quantities between which uncertainty relations hold, and in fact for the reason that the sum of two such quantities is not immediately defined at all. And since the sharp measurement of one of them excludes that of the other, so that the two quantities cannot simultaneously assume sharp values, the usual definition of the sum of two such quantities is not applicable. So she in principle repeats what von Neumann already has said. But then Grete Hermann goes on, and this I think is what is really remarkable. She now discusses von Neumann's remark about quantum mechanical formalism, and she starts to interpret these quantities which she uses and to figure out why this is not a necessary assumption in general. So she says that we have this, she repeats in principle this argument of von Neumann, and then she says the interpretation of this quantity, and I've written this quantity here in the way as it is written in Grete Hermann's text. It's essentially the same as the bracket notation which I've written above. So the interpretation of this matrix element is that of an expectation value of R in an ensemble which is prepared in the state phi, and phi, as we said, was a wave function. Mathematically a wave function, and physically an ensemble of systems which were prepared in a kind of pure state, for instance, using maximal observables. And then she goes on and writes, if phi can be split into sub-ensembles, this is what we want to prove in principle cannot be done, but suppose it could be done, for instance, with respect to new variables, then there's absolutely no reason why this interpretation should also hold for the sub-ensembles. And then she goes on writing, keeping this assumption, one has implicitly absorbed in the interpretation the unproven assumption that there can be no distinguishing features on which the result of the R measurement depends. She later, makes the remark that, of course, there can be additional variables. I mean, there's a nice example in physics, that's spin, for instance. Until 1924, we didn't know about spin, and then suddenly there was a new variable, spin. But this is also described in terms of the quantum mechanical formalism. So we use vectors in the Hilbert space to represent spin states, and we use Hermitian operators to represent the observables. So this is not what she means. What she means is, can we extend quantum mechanics by variables for which these properties do not hold? And here she says, no, von Neumann's proof depends on this linearity assumption. The linearity assumption, however, in a certain way already puts in the assumption of quantum mechanics. And therefore, well, she calls it circular. One can argue whether circular is the right word, but at least it excludes, in principle, any other theory which is not essentially based on the quantum mechanical formalism. So this is, I think, the remarkable part of her critique. It's not simply saying von Neumann makes this linearity assumption and this is not necessary or this is not justified, but she analyzes why it is not justified and where exactly in principle one could expect that maybe something different happens. And this indeed was the case later in the examples of John Bell and David Bohm, that this exactly this, what she writes here, that the subensembles which can be constructed in these theories do not satisfy this linearity condition. Now I come to this 8th paragraph, as I said, which is still for me a little bit mysterious. She writes that essentially if quantum mechanics denies the existence of additional features, that is, if it claims to be complete without being able to completely explain the outcomes of measurements. And it's interesting to see here that she uses the word explain and not predict anymore. But that she says complains the outcomes of measurement. It contradicts the principle of incompleteness of experience. I must admit, I do not know whether such a principle is generally known in philosophy, principle of the incompleteness of experience, but I can imagine what she means. And in principle, the first 7 paragraphs, as I said, are devoted to proving that such a claim of quantum mechanics is wrong. But now comes this switch, a change of strategy, you call it. The only reason, she writes, why quantum mechanics can justifiably deny the existence of such additional features is that all causes for explanation are already known. And now she tries to justify this statement that these causes for explanation are already known. And in this context, she uses a work of Carl Friedrich von Weizsäcker from 1931. Actually, it's quite interesting for me to see that the Carl Friedrich von Weizsäcker is the only author here of that article. It's not Weizsäcker and Heisenberg, even though Heisenberg surely had a big contribution to this. Von Weizsäcker was 19 years old when he wrote this article. He just had joined Heisenberg's group. So it's a little bit, one sees a little bit change of publication politics here, that Carl Friedrich von Weizsäcker is the only author. So he makes an analysis of how can one observe the location of an electron by using a microscope. It's sometimes called the Heisenberg microscope, sometimes called the Heisenberg-Weizsäcker microscope. And the setup is quite simple. The setup is that we have an electron, which, however, can move only in a plane. The electron is hit by a photon. The photon is scattered. And then there is an optical lens and a photographic plate where the photon is registered. And the article is quite technical. The article essentially makes the quantum mechanical calculation of this process and wants essentially in the end to show that the quasi-classical explanations which we can give using classical wave optics or even to a certain extent geometric optics, that they still give the correct predictions. But essentially it's a quantum mechanical calculation. So how is this done? The determination of the position, for instance. You describe the incoming photon by a planar wave with a certain momentum. The planar wave coming in from the right is scattered the electron from the electron, which has a certain position here, point X. And so there's a spherical wave emanating from that point. The spherical wave comes to the lens and is focused again. And if the photographic plate is in the image of plane of the object, then the focus will be exactly at one point, which corresponds to that point X. So from reading this point here on the photographic plate, we can determine where is the point X. And the state of the electron plus the photon after they have interacted here can be described as a superposition of possible positions where the electron could be. So up to now, we haven't registered the point on the photographic plate. So it's a summation of possible positions, the electron being at one of these positions, and the photon is described by a spherical wave which emanates from this position. So that is the state of electron plus photon after this collision. We can describe the same in terms of geometric optics. This comes in modern terms to the quantum mechanical description as sum over possible paths. So there's the incoming ray, there is the final point where the ray or the photon hits the photographic plate, and we have to sum over all possible paths which hit the electron at point X and which end up here at these points. So we sum over all these paths which I have indicated here. And these paths do not have a well-defined momentum. The momentum would be a well-defined direction of the photon. But here we have all directions, and that is the argument essentially of von Weizsäcker, that we do not know the momentum of the electron after it has been scattered, the photon scattered, because there was an unknown momentum transfer to the electron, and so we can only know the position but not the momentum. A second description enters if we change the photographic plate from the image plane to the focal plane of the lens. If a wave hits the focal plane here, then it was a planar wave before it entered the lens. So a planar wave entered the lens, and then it is focused here to one point. And now the description is a slightly different one. We have the incoming photon as a planar wave, and we have the reflected wave now from electrons, which the electron is distributed essentially in this plane. It doesn't have a perfect position. And so there is a planar wave scattered, and this planar wave is focused here. And now we can speak of a definite momentum transfer. The incoming photon planar wave has a definite momentum. The scattered wave has a definite momentum. And that it means that there is a definite momentum transfer to the photon, to the electron. And so the state of the system, electron plus photon, is described now as a superposition of momenta, where the electron has a certain definite momentum, and the photon has a certain definite momentum or momentum difference relative to the incoming photon. And so depending on whether we put the photographic plate in the focal plane or in the image plane, we can measure either the momentum of the electron or the location of the electron. And again, we can use kind of summation of history, representation of quantum mechanics, saying, well, we have all these incoming rays. They are scattered from electrons, which can be, or from an electron, which can be everywhere here. but they all are combined into one point here on the focal plane, and they give us a definite momentum transfer from the incoming to the outgoing photon. And so we know the momentum which the electron got, but we do not know its position. Now, what does Grete Hermann now do with this situation? In principle, one can say in her discussion of that experiment, she touches upon all the modern keywords which we use in the discussion of a measurement process. Of course, she doesn't use these keywords explicitly because partly they were not existent. Entanglement, for instance, was a word which in beginning of 1935 didn't exist. It was coined by Schrödinger in his response to the EPR article, and the EPR article came later after her 1935 paper. So, but she uses, in principle, the concept of entanglement. She uses the concept of pointer basis, again, a word which didn't exist at that time. She uses the concept of Heisenberg cut. That is the question whether a certain object, like in this case, the photon, is considered the measuring instrument or is considered something which has to be described quantum mechanically as part of the system which is measured. And well, you can argue whether already the concept of delayed choice is in here. Of course, she doesn't mention that explicitly, and she doesn't even say that that after the interaction between photon and electron has been taken place, one can choose where the photographic plate is. That would be really delayed choice. But in principle, certain ideas of delayed choice you find already in Grete Hermann's article. To give proof of some of these, for instance, entanglement, she describes what is entanglement. And entanglement she describes as, let's quote from her article, 1935 article, finally, if one sets up no photographic plate at all, but allows the light quantum to pursue its path without detecting it, then one obtains yet a third, though not in the same way intuitive, description of the state after the collision. In this case, the physical system composed of the light quantum and the electron is assigned a wave function that describes a linear combination. Each of its terms is the product of one wave function describing the electron and one describing the light quantum. Through this linear combination, the light quantum and the electron are thus not described each by itself, but only in their relation to each other. Each state of one is associated with one of the other. And I think this is a perfect description of what entanglement means. As I said, at that time, the word entanglement didn't exist. The Heisenberg cut, and maybe I will not read this here, but here she describes that one and the same system, and in principle, the photon in the example which we discussed before is such an example. One and the same system can be either the measuring instrument or it can be part of the quantum system. And so we can decide where to put essentially the cut between quantum and classical description. And what she describes here is that on the side of the measurement, we use essentially the classical description. And that is what Carl Friedrich von Weizsäcker has shown, essentially, that the photon can be described classically, as we saw, by classical wave optics, and one still gets the correct result. So one is open whether to describe the photon in terms of quantum mechanics or in terms of classical concepts. And that is essentially related to the Heisenberg cut. And I think Guido and Elise Kral have a very nice paper on different versions, let's say, of no-go theorems. Why hidden variables cannot exist. In principle, many physicists at that time had their own version of the no-go theorem. Heisenberg, for instance, he wanted to use this cut. Heisenberg argued in the sense that The quantum system alone is deterministic. It's a deterministic equation, the Schrödinger equation, if you want. On the classical side, we also have determinism, whether you use Newtonian mechanics or other description. So the indeterminism can only be where the classical and the quantum meet, so at the cut. But as the cut can be shifted, where then should the variables, the hidden variables, be? So many people had their own arguments of why hidden variables couldn't exist. And I have the feeling, to a certain extent, that Grete Hermann surely discussed this with Heisenberg, and that this enters here, this argument enters here a little bit in her 1935 article. I mentioned pointer bases, and that's also something which Grete Hermann makes very explicit, that depending on what she calls the observational context, we have to use different expansion of the state of the electron plus photon. If the photographic plate is in the object plane, then the expansion is with respect, let's say, to eigenstates corresponding to the location of the electron at a particular position, and a spherical wave for the photon emanating from that position. If the photographic plate is in the focal plane, we have to expand the same state in terms of different variables, namely momentum eigenstates. So the electron having definite momenta, and the planar wave of the photon now having a definite momentum. And so that in principle touches already the point basis problem. So she comes to the conclusion why quantum mechanics is already complete by saying that the information we have about a system, or in this case, why it is not causal completely, the information we have about a system is always relative to an observational context. That's also a very, very early version of relational interpretation, which later was also put forward by Bohr, by Niels Bohr. But this relation to an observational context, she says, is not sufficient to predict what will happen in a different observational context. After a measurement has been performed, we can explain, at least to a certain extent, that is my insertion here, because I believe that we cannot always explain why a particular result was observed, at least not completely. But I think Grete Hermann was at that time, at least in 1935, when she wrote that paper, she was convinced that after a measurement has been performed, that we can always explain why a particular result was observed. And she refers to that example she had discussed, the Heisenberg microscope. And finally, during the scattering process, and that is, I think, a very important observation, during the scattering process, so when the photon and the electron interact, all the information about classical properties, all the information about the position and the information about the momentum are transferred from the electron to the photon. Because now, as we know, we decide by putting the plate into the focal or into the object plane whether to measure the momentum of the electron or the location of the electron, and all the information is now in the photon. So in that sense, she can argue in favor of completeness by saying that all this information obviously has been transferred, and the problem that we have an observational context now is shifted to where do we put our photographic plate. So let me come to the concluding remarks. I think what is remarkable in this article is that the philosopher in Grete Hermann asks really the right and precise question. And the mathematician in Grete Hermann is then able to answer them with precision and rigor. And it is this remarkable combination of philosophy and mathematics, which I admire in that article, which you do not find, for instance, in von Neumann's book. That's mathematically very precise, but it's not really, it doesn't always hit the right questions, and which you do not find in many of the physics texts. I think the article is still worth reading. It's not only worth reading for a historian of science or a philosopher of science, but it's, for me, for instance, worth reading as a teacher. It may not help me very much in doing research, but when I teach quantum mechanics to students, all these questions which he touches here in principle come up, and it's worthwhile to rethink all these questions. And in that sense, I think this is also a remarkable article. And finally, as I mentioned several times, I think that there's much more research necessary to illuminate some of her argumentations in that article. For instance, as I said, this shift in her argumentation from requiring predictability to the statement quantum mechanics is already complete, but is not able to predict the outcome of measurements. So that brings me to the end of my talk, and I thank you very much for your patience.